Hello and welcome, dear friends of grinding technology. We are back with the second edition of our Sunday Tool Talk. But before we dive into the topics, let me first say one thing. Thank you so much for your positive feedback. You made it clear that this kind of content was long overdue, and that's exactly why we are going to keep this format going. Alright, now let's talk about today's content. I've picked out 3 exciting topics for you, all based on popular demand. First up, NUMROTO know-how, a quick insight into the up and down cutter module. Then, equipment and technology, hydraulic chucks versus shovel and collets. And finally, Q&A, watch out, fake application engineers. Topic Q&A, fake application engineer. A friend of mine, a business owner from Germany, recently asked me, Daniel, I am looking for a good NUMROTO application engineer. Do you know someone? Can you recommend anyone? And what should I look out for? It was a great conversation, and I asked him if it was okay to share this here. He said yes. So here are my thoughts. What is and what isn't an application engineer? In any company that uses NUMROTO, the goal is always to represent the grinding process as safely and efficiently as possible. And that's exactly what an application engineer has to ensure. For simplicity, I'll just say application engineer from here on. So, what makes a real application engineer for me? First and foremost, they need years of experience in tool manufacturing. If you only have some years in manufacturing, you will never be a real application engineer. It's just not possible because you just lack the experience. You need at least 10 plus years. And not only, in mass production, standard drills, like small batch special tooling. That's where it's, like you learn a lot from special tooling, from setting up 2 or 3 tools instead of making 50 or 100 or 500. Those are different worlds. They must be able to independently develop and optimize even complex processes. What I mean with that is exactly that. The customer has a special request. You never did that tool before. So it's your duty as an application engineer to sit down and solve that problem. And you don't have anybody to ask because you are the man. That's your job and you are the application engineer. And, even if you take like 2, 3 or 5 days or whatsoever, come up with a solution and test something. And if you don't know it, then, reach out to your colleagues or come up with a process and try something. So a real application engineer can develop and optimizes even complex processes. They need a deep understanding of tool programming. So just important as it is how to grind tools, it's also important how to program them. You need to know the features and how everything is set up, how things work together. Because if you write your program wrong, then you change something on one end, it might change on the other end because some people are not fully aware of how the NUMROTO program really works. Sometimes you change something here and then here it will change as well because those two things are actually connected. And if you don't know it, you have a problem. So a real application engineer, he knows all that stuff. And a true application engineer is the central pillar of the company. They test new equipment like wheels, collets and machines. They ensure NUMROTO programs run as intended. If something isn't working, they gather the necessary data and adjust the technology at its core. So means you write a program You send it out to the machine, and then it's your responsibility to make sure that program is working. If you can't do that, you're not an application engineer. Also very important for me, they should be approachable, helpful, and above all, open. Nobody likes an arrogant and cocky application engineer, who walks around and, just pretends I know everything. And this is like, the more you know, the more humble you need to be. And a real application engineer is, just like I said, he is approachable, helpful, and above all, open. So a real application engineer should also support the sales team when needed. Sometimes they have questions, nobody can answer them, or they look for ways, or support. So just help them. That's like a real application engineer. In my opinion, is like the glue of the company. He needs to be a little bit everywhere. If the company has its own development department, they coordinate testing and implementation. If there is no development department, the application engineer is responsible for developments and tests. Then he has to do it. Not every company has 2, 3, or 500 employees. So in a small company, a real application engineer is doing the testing. So he will be responsible for R&D as well. A real application engineer, they can train employees, manage production, and make critical decisions. So to me, a good application engineer is supervisor, machine operator, programmer, R&D engineer, trainer, and production manager, all rolled into one. If someone checks all those boxes, then yes, they're a true application engineer in my view. So that's, like the perfect application engineer. So on the other side, how to spot a fake application engineer. And I think there are quite a lot on the market. So it's not I'm not an application engineer police, and say, oh, you can't do this and blah, blah, blah. You're not an application engineer. But most of the time, like a bad application engineer, you can spot them very easily. And the following signs are very clear. They have no clue about feed rates, cutting speeds, or grinding cycles. They avoid such questions like, how much material can I remove with this wheel? They say, I don't know, and that's up to you, and blah, 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 up to your experience. That's nonsense. Like a real application engineer, he knows all that. That's in fact. Fake application engineers, they write programs that always need tweaking at the machine, never work properly, and no one on the shop floor trusts. So that's the worst thing what can happen to like a modern manufacturing place. If you have someone writing programs and then they get to the machine and all the employees say, his programs, they are not they never work, so I always have to change things, and this is just pure poison. So you might end up with different geometries and so on. So bad things will happen if you can't trust the program that is sent to the machine. And a real application engineer, he understands that. And if he has a problem, then he need to reach out to the machine operator afterwards and say, hey, listen, did you had a problem? Yes or no? And what do you think could I improve? And then so step by step, so it's a continuous improvement process, and then he gets better. But a fake application engineer, they're not interested in such things. So basically, meaning they haven't understood the underlying technology. All right? So there are a few, you change a few things and then, they just crumble. Also, fake application engineers, they like to give vague answers. They are never direct. Because they don't know, and then they feel insecure and they say, yeah, well, maybe here, maybe blah, blah, blah. A real application engineer, he looks at the problem and said, okay, this is my solution and I stand behind it. And if not, I was wrong, and then, we fix it later or we improve it together. Fake application engineers, they usually, you can poke them and they never give you like a direct, clear answer. Also, a fake application engineer can't adapt the program for different machines. That's always a problem if you have different machines in the company, and you have a having fluting process, for example, like on a powerful machine, and then you need to adapt that process for a different machine type. Let's say half the spindle power. A real application engineer, he will just sit down, said, okay, and he already knows the maximum removal rate. You can just, if you know how, you can just go into your 3D and fire all that stuff out, make some tests. But a fake application engineer, he's not capable of such things. It's fake application engineering. So, and the last point I have, a fake application engineer, they know little to nothing about how tools actually work, the function. There's no concept for margin width, for back taper, for cutting angles, for tool design. They basically just type the things, like the data given, they just take it and try to do it as good as possible. But this is just not like a real application engineer. He has at least he has to know fundamental ideas of how tool work, like reamer, end mill, drill, step drill, core diameters, back tapers, and much, much more. Other red flags for fake application engineers, they think they know everything, they don't share their knowledge, and they always resist change and slow things down. So that is my opinion, like real application engineer, fake application engineer. Of course, it is difficult, to really become a good application engineer. But if you're honest and if you try, over the time, you will be a good application engineer. But usually you start out small on the machine or, grinding manual, get a feeling for it, and then you grow into that position. You don't fall from the sky. There has never been a master just falling from the sky. This is just not happening. So, conclusion, yes, there are great operators and great programmers, but a good application engineer is much more than that. They hold the entire system together because they understand the process. They work daily to improve, maintain, and evolve them. They are the glue that keeps everything together. This is also the person you search if you want to open a new production site, start a new product line, or plan and lead important projects. And of course, people like this need to be developed and supported. Just like I said, they don't just fall from the sky. All right, guys, let's talk about the topic equipment and technology. Hydraulic chuck versus Schauble collets. So people often ask why one and not the other. There are a few key differences, and today we take a closer look at them. So the most important pros and cons. Functional principle difference. So they are like day and night. They work on a completely different background. So the technique, the style, like the principle on a hydraulic chuck is different. So the hydraulic chuck is using oil that is pressed into an expanding sleeve, which then compresses the collet and the tool shank, right? So oil is used, and you can apply that manually or automatic. That doesn't matter, but the system is different. So you press oil into an expanding chamber, and that expands, and then you press, the collet, and the tool in the collet is clamped. So, however, with the Schaublin collets, a slitted, tapered collet is pulled onto a cone to clamp the tool. So that is different. So you have like a drawbar and a collet, and the collet closes through the through that motion. So it works different. It's a different type. Okay. So advantages of the Schaublin collet. What I see is they open slightly wider, making them safer for automated loading. So that means those Schaublin collets, they open wider. So you have a lot more tolerance for the tool to enter, compared to the hydraulic chuck system. Those collets, they are more or less exactly the same diameter like the tool shank. They are not expanding to nowhere. So basically they are very, very precise. And this can be a problem, especially for the loader run. You never know if you have, heavy tools, and then the tool is not like, it's tilted a little down, or sometimes also, which can be a problem if you have like regrind, and then the shank of the tool is not cleaned properly. You have some leftover cooling fluid or material that sticks to it. This can be a big problem. So for lights out production and automatic loading, I see a benefit personally for the Schaublin collet. Also, a big advantage is the clamping force extends all the way to the front, making then the top choice for tools like micro and miniature drills. They need to be clamped very close to the end. What I mean with that is, like in micro tooling, usually you have like a 4 or 6 millimeter tool, the shank, and only the front is the small part. So, but in the end, to make it more accurate, the tool is just driven by clamping a few millimeters, and in the front, the tool is supported by kind of a V-block or like a half shell. And you can't do this with an hydraulic chuck. It's not possible. Because the hydraulic chuck, the first area is a dead area. But however, disadvantages, what I see for the Schaublin collets, they shouldn't be clamped without a tool. Otherwise, both the collet and the holder can be damaged very quick. But to be fair, hydraulic chucks also shouldn't be clamped empty, but it seems to be less critical. I see this quite often in like all sorts of companies, and also like usually the manufacturer says for the hydraulic collets only use the system if you put the tool like to 100% in. But in reality, I see this all the time. That they're just clamping through like 50% from the recommended length. So it seems to be less critical here. Otherwise, everybody would have broken hydraulic chucks. Other disadvantages, what I see for the Schaublin collet, in special applications, they can be a bit inconvenient since you can't remove and reclamp the tool without losing its position. It's basically the whole system is just you clamp it or you unclamp it, and then you get the tool out and in. So, but this is a problem for special tools. If you want to set up a special tool, like I prefer to take my tool out with the holder. Preferable like a HSK holder, and then I take the tool, I measure it, I bring it back in, and then I can work with probe values. That's the way to go, at least for special tools. And this can be a bit problematic for the Chaublin collet. However, there are certain techniques you can learn, so you can make your way around it. Let's put it that way. Maybe we can talk about that later, but there are ways. But I prefer, like for special tools, to take the tool out and put it back in without losing its position. And for me, that's the HSK interface. So let's talk about the advantages of a hydraulic chuck. In general, more precise due to the high precision manufacturing and the fundamental different working principle with far less movement in the system. If you press that oil into that chamber and basically it just closes, done. So the force is applied in a completely different way. Also, what I noted here, tool can be easily removed from the holder via HSK interface. I just talked a few seconds about this, and this makes it great for special tools, right? So there are a lot of holders which are connected, by like kind of an adapter plate, or you have just, that HSK interface like one-on-one on the machine on your A-axis. There are different setups. And this is great, for special tools. I absolutely love this, to have my tool in, HSK interface, manual holder, and I clamp it, make my adjustment, take the tool out to the measurement machine, make my measurements and bring it back in and continue grinding without losing the position. So this is fantastic. But also great for automated systems. There are solutions for automatic chucks as well. So it doesn't mean that you have like an hydraulic chuck and it's a manual chuck only. So there are, of course, automated solutions as well. And I'm sure you all know about this. But however, different system, comes with disadvantages. And we talked about that before. And that's, for me, the biggest disadvantage of that hydraulic chuck system. The front area remains always a dead zone with no clamping force, right? So, and there are some cool pictures which I might show to you. And this illustrates very well, this chamber with the oil and how it works. So, and it's clear, like the first area is a dead zone. There's no clamping force, and this can be a problem for special applications. Disadvantage: tool should always be inserted as deep as possible. That's we talked about this. Just the problem with the dead zone, but also that that chamber it will close around the collet, and the problem is if you only clamp the tool to 50%, you just maybe, let's say it's recommended to put it in like 22 millimeter and you only do it 10, the force applied on your tool might not enough to hold it during grinding, especially if you have like a heavy fluting process. It can be problematic. So keep that in mind. Also, and the tools with large clamping flats may sometimes be pushed out of center, and this is also caused by the system of, pushing oil into an expanding chamber, right? So it will close evenly around the collet, but if you have in the collet a tool with just a half tool, which you have like a huge flat, and sometimes you have that. So which will happen is it will close evenly, but here's no material, so your tool will slightly be pushed out of the middle. And this is important if you work really accurate. If you want to work to the micron or special tools, keep that in mind. Or if you encountered such problems, it most likely it comes from this problem. There is a way around, but this is not the right time to talk about it. Because now we want to talk about precision and adjustment, hydraulic chuck versus Schaublin chuck. For me, they are more or less the same, so it really doesn't matter which system you use. Each system has to be, put on your A-axis, and you have to, adjust for run out and wobble. So the system is not really so much difference. But anyways, I wanted to share two systems which are really famous, and that's of course the Schaublin SAS system and the GDS, the MuGrind or microgrind. So both can be adjusted very precisely. They are great systems. A lot of people use them, and so that's it. For the hydraulic, it's like I said, it's more or less the same, but precision and adjustment, I think with those modern systems, it's of course it's all about run out and repetition. They say like hydraulic chucks are always better, but who knows? So I think personally it comes a lot down to how to set it up, how to maintain, and this is important, and like I said, it's for me difficult to say which one is better. I mean, personally for me, if I do special tools and I need like run out to the micron, I still prefer the hydraulic chucks. Also, there are some chucks on the market. You have like a second pair of adjustment screws. That's it calls the Tendo Zero from Schunk. So it's a manual system, and you have on that chuck you have 4 more screws. So then you would have more or less 4 screws on the holder mounted on the A-axis, and on the chuck another 4 screws. So this might be also something you want to have a look at. But I think that should be it. I don't want to make it longer than necessary. There are of course other solutions out there, but today we're focusing only on these two. No need to dive into every variant. So I hope I could shine a little light on the most important key differences. Okay, topic NUMROTO know-how. Quick insight into the up and down cutter module. Just a short overview of the up and down cutter. So up and down cutters are mainly used to ensure a clean surface finish on both the top and bottom side of a workpiece. These tools have one section where the spiral cuts downwards and the other section where it cuts upwards. The opposing spirals must always overlap at some point along the tool to ensure a clean cut without leaving holes. So this is more or less the whole principle of an up and down cutter. The problem was, before the up and down cutter module, you had to do this by hand, which was quite difficult, But anyways, now there's the up and down module, so you don't have to do this by hand anymore. There is just like a clean interface with presets for the most common variants, including 2, 3, or 4 cutting edge pairs. So it's way easier. It's really user friendly, and most important, the way you program it has completely changed. So you can now actually see the result based on your inputs like wheel angle, core diameter, rake angle, and clearance angle. And thanks to the recent update, it's now also possible to regrind those tools efficiently. So you will really like it. And so what I'm gonna do now is I'm gonna take you with me to my PC, and we're gonna program like nothing super complex, maybe like an easy tool, 2, 3, maybe 4 flute. And because I want to show you the way how that module works. You have quite a few interesting input areas, and you can program either with the overlap amount or with fixed cutting angles, and I want to show you the fields because you have a lot of data you can put in, but also you can get out. So you can program the first cutting edge length, the second length. You can program with fixed values like cutting angle or rotation angle, but you're gonna see it for yourself. So, all right, I'm sure you're excited to check it out. So let's jump on the PC and program a simple example together. See you in a second. Okay guys, welcome back. Now here on my computer, we are already in the end mill package. And the end mill package is the right place to jump into the up and down cutter module. Now you see that here. So if you bought that option, then you can just choose that. And let's say manufacturing. What we want to do here is a simple tool. So it's basically 2 to 10 millimeter. So here is already, so that's basically the place where all the magic happens. And so I usually work with cutting edge length helix 1 and overlap amount. So let's say 10, 25 and 1. Then nothing too crazy, something that works. I know that tool will cut pretty well, but basically the whole idea is to have that wizard, that up and down wizard, where you can just type in what you want and all the calculation will be done for you. So as you remember, or if you ever have programmed an up and down end mill by hand, this can be quite complicated, especially if you have more than 2 edges, if you have 3 or 4, and that module will support also 3 and 4 cutting edges. But anyways, so what we've done here is we have a cutting edge length here from 10 millimeter, overall, total 25, and the most important overlap amount 1 millimeter. So now I just go to next. Everybody knows that this is just standard NUMROTO. And now we end up in our main menu here. And maybe one thing before we start. So the up and down module would not have be possible without the flute X operation. So if you visited the grinding hub or the IMTS, or if you frequently talk to somebody from NUMROTO, you already know flute X, or basically all X operations, are indeed the new operations already coming from the NUMROTO X. And based on that new technology, the up and down cutter module is possible. Okay, let's type in some wheels. I basically know the wheels, what I need. Okay, need a gash wheel here. And another cup. Okay, so now I basically programmed all the wheels I need. Then I can go into my geometry back, and now I can update, calculate dependent values. So basically what it does, I cannot calculate anything if I don't have the wheels and my geometry data. But now that I said, okay, I want 30 degrees helix, 12 degree rake angle, core diameter, overlap amount, cutting edge length, and so on. NUMROTO will be calculating everything for me, and that will just happen here. So, okay. Now I already see my cutting angle in the back is 17 and in the front it's 14. So I don't like that very much because I always go for equal cutting angles and lowest cutting angles. So I'm probably much better off if I change that to 13 and calculate it again. Okay, now it's 11 and 13. I can live with that. Say okay. Before we start, because I already know I need grinding position 2 here and over there. And now, okay. Yeah, that's completely normal because we changed the position of the wheel. And NUMROTO knows, operator changed something, I need to recalculate. But you don't have to go back into the geometry window. So I just say yes. Okay, so that's it. Let's say start. And here we go. So I think that looks pretty nice. Maybe my flute is a little long here, but that's an easy fix. And yeah, so that's basically the whole process of programming and simulating this up and down tool. And everything is already in spec, right? So remember, cutting edge length, overlap amount, yeah, great. Maybe I want to change something here. So I don't like that body clearance, that's a little long. Also, probably I would like to have this a little wider. Here the body clearance is basically attached to relief number 2, to the width. Yeah. Okay. And that is something, I really like that. I mean, I really love that up and down cutter module because I know how complicated it was, to do that by hand. Basically, you need to go into the end mill package and then you have 2 different helixes and you need to copy reliefs and all that stuff. Yeah, that is complicated. So now it's very easy to adjust for all kind of geometries, and even if you have fluctuations with your diameter in the back, because you have a different grinding spindle position, so your diameter can change. And I can just say, okay, I measured it maybe 20 microns too big or too small, and here you go. Just all the operations will follow. Or even I could say, yeah, well, let's try something different. And I want to have not 30-degree helix in the back. I rather would have 25, or I would like to have only 10 in the back, from my rake angle, but more core. You can all do that. It's really, really user friendly. And just like I said, even like an experienced programmer, especially if it gets a little bit more complex, you would have problems to do that by hand. And especially for that reason, so I prepared like an old program what I had, and I made everything by hand. And this is indeed the program I used to create a 6-fluted up and down cutter. And you already see, whoops, how much operations were used to create that geometry. So, and now just imagine, I need to change something, because at the end it's all about making a good tool, just having like a good program or I don't know, like a nice looking simulation, it's not helping your customer. It's all about making good tools. So, and setting up a tool like this, adjust for it, basically dialing it in, that is complicated, and you need to know what you're doing. And the problem in most companies is you have one or two guys, they are capable of doing such things, and the rest are struggling if you don't have the proper training, of course. But those days are over, because now the up and down cutter module is on the market. It works. I really like it. Even, if you insist on program it like the old way, you can still say, screw all that. I rather program with like the way it used to be, with fixed cutting angles. But also here, now you have the option, to actually just see the result. You don't have to play around in your 3D sim and just change things on, I don't know, just on trial and error. So even now, I can just say, okay, I want to work with fixed cutting angles, and now I can already see my overlap amount. Yeah, this is new. And like I said, the up and down cutter module is user friendly. It works. Yeah, and I would try it. Just go to your machine manufacturer, ask for a license, try it, work with it, and you will not regret it. All right, that's it for today. I hope you enjoyed it. Feel free to leave a like, share this episode, or subscribe to our YouTube channel. And if you want to learn more or are looking for real training and know-how for yourself or for your company, just reach out, because we are your partner for practical training and effective solutions.